refresher on what we have studied up to this point. Last semester we looked at doing some mole calculations. I'm not going to go through all of this, but basically we said that if you can get to moles of a substance, you can go back and forth between moles and grams. You can do that by using what we call GFM, the gram formula mass, molar mass, whatever you want to call it. Or you can go back and forth between moles, and then this one over here is number of particles. And we used Avogadro's number, which is 6.02 times 10 to the 23rd. We're going to see that we don't do this much in stoichiometry, but which is what we're studying now. But that's what we learned last semester. And then we just aced our test on chemical reactions. And here we saw that there's 5 main types of chemical reactions, and what that information does, we can now put those two together and really think about what this information tells us. If you have this reaction right here, where you have hydrogen plus oxygen yields water, we see that we can say, well, 2 molecules of hydrogen plus 1 molecule of oxygen gives us 2 molecules of water. Or we could talk about that in terms of AMU, which isn't so common. Or, this is helpful, saying 2 moles of hydrogen plus 1 mole of oxygen yields 2 moles of water. We could even break that down to mass. If you know your moles, you can convert that to mass. So you can convert it to grams. 4 grams of hydrogen plus 32 grams of oxygen yields 36 grams of water. Notice that your mass is conserved in that. So a balanced chemical equation really tells us a whole lot of information. So what we're going to do today is we are going to be able to go from amounts of one substance to amounts of a different substance because we're using our balanced chemical equation. In other words, we're using our coefficients in that equation to give us our mole ratio. So it gives us the ratio of moles. Okay, so this is the information that you guys have on your handout in front of you. I'm really going to blow through this pretty quickly and get to the examples. I think that's where you guys will have better learning on this. So, gives us a reaction. Again, this just reiterates what we said. We could say that, yeah, that's 3 molecules of calcium nitrate, or you could talk about it as being 3 moles of calcium nitrate and what we yield from there. And here, of course, it's not really worth it, since it's such a small thing. We don't really want to talk about it in terms of molecules, and that's why we use moles. And then it starts getting through to the calculations, and you've got these calculations right in front of you, so I'm not going to go through them step by step. But what I want to really point out to you guys is once you have that balanced chemical equation, what I'm going to ask you to do, and this is when you'll have the most success to do this, is if you write down the information from your problem here underneath your balanced chemical equation, that is just going to redirect your eyes and it's going to show you everything that you need to know. So for example, it says, how many grams of sodium phosphate? So I find my sodium phosphate and I would put question mark G because it's asking how many grams of sodium phosphate are required to react to form 23.4 grams of calcium phosphate. So 23.4 grams of this. Well, I have just written everything that I need to know right here, so I don't have to read through that verbiage anymore. Everything I need is right in front of me. And then the workout of the problem is given to you in your handout, and I'll let you guys look at that on your own time because now we're going to do our own problems. Before we can do any of these, what do we always have to start with? Always, always, always. Thank you. Balanced equation. You got to start with that. And then what we're also going to see in this today is that we're not always going to be going back and forth just between grams and moles, but we also want to think about concentrations for our solutions. So how do we measure concentration? What unit did we call that? You guys remember that from last semester? Molarity. So big capital M equals moles per liter. That's going to come back in this unit as well, so you've got to remember that. Okay, so that takes us to our mole map, and with our mole map, these are mole calculations. What we did last semester was we just looked at one of these and we said, hey, if you've got it as grams, you can convert to moles by using your periodic table, your gram formula mass. Or once you've got it as moles, you can convert to particles, or vice versa. You can convert from number of particles to moles. But you can do that by using Avogadro's number. Now we're seeing that, again, you're not really going to use this too much in this material that we're talking about now, but we are going to be wanting to go from moles of one substance, which I will call A, to moles of a different substance, which I'll call B. So this would be grams of A, this would be grams of B. And in order to do that, we want to be able to use this guy right here. We want to be able to use our mole ratio, which is really just saying that you want to be able to look at your balanced equation and use your coefficients. There, that's what we're going to do to go from moles of one substance to moles of another. So that's that mole ratio step. That's really the only new step in this. So first example that we have. How many grams of nitrogen are needed to react with excess? So I know nitrogen's a reactant. React with excess hydrogen. And the reason it gives this is because later on, the reason it says excess is because later on we're going to be having limited amounts of something. And so we're going to have to figure out which one we run out of first. But right now it'll just say things like it's given in excess. And we know we're going to produce ammonia. How do you write ammonia? NH3. It's not ammonium, it's ammonia. So it's NH3, not NH4 with a plus 1. So then we come back and balance. So we'll put a 3 and a 2, and that looks good. So balanced chemical reaction. Then, as part of that first step, I really want to write that information underneath. So it says how many grams of nitrogen. So question mark, and a question mark's not good enough. Make sure you write the units of grams, because we're going to be looking for all sorts of things eventually. So I want to find my grams of nitrogen that's needed if I want to be able to produce 157 grams of my ammonia. So now everything I need is right there for me, so it makes it real visual. Okay, so I'm going to go ahead and start with my 157 grams of ammonia, and I'm going to flip back to the mole map here. So I'm starting with grams of one substance, and I want to go to grams of a completely different substance. So if you can think about where you're starting with grams of one substance, what do you then need to go to? Moles of that substance then? No. Moles of one substance, then go to moles of the other substance, then grams of that other substance. So this is my pathway that I'm taking. I'm starting with this, I'm going to this. So you can always think about just going through that mole ratio step when you're converting from one substance to another. Okay, so I've got it as grams of ammonia. That is not what I want. What should I go to? You already told me. It would be moles of ammonia. Now, I guess I don't have to worry about, oh yes, I do. I'm sorry, I'm looking at the wrong one. When I calculate my mass here, and I'm bringing this up because this is a common mistake that people will make. I know that 1 mole of any substance is equal to its weight in grams. So when you come over here and look at this is what I'm adding up. I do not care about this 2. Never deal with your coefficients during a mass step when you're trying to figure out the mass of something. So all I'm going to worry about is the fact that I've got 3 hydrogens and 1 nitrogen. So when I add those up, I get 17.04 grams for every 1 mole. Do not multiply that times 2. So you're just doing the formula mass of a mole of ammonia, NH3. Now you've gotten rid of your grams of ammonia. You've got it as moles of ammonia, but yeah, that's not what you want. You don't really want it as this stuff. You want to come over here to your nitrogen. So you want to get rid of your moles of ammonia, and you want to go to your moles of just nitrogen. In order to do this, what number is going to go up top? 1. What about the bottom? Awesome. Because we looked at these values right here. This is that mole to mole transition step when you use your mole ratio. So now we have gotten rid of the moles of the stuff that we started with, and we converted to the moles of the stuff that we're looking for, moles of nitrogen. Well, it doesn't ask for moles of nitrogen, it asks for grams of nitrogen, so we're not done yet. We have to keep going, get rid of those moles of nitrogen, go to grams of nitrogen. 1 mole of nitrogen has what mass? Not 14. 28. Is it 28.02, I think? Let me just check real quick. Actually, yes, it would be 28.02 grams. So now we have our answer as grams of nitrogen. All we have to do is plug it in. Everybody has their calculators out. And how many sig figs are you going to round to? 3? Because we've got that. 3 sig figs, so our final answer is... anything? 129 grams. And instead of just writing that, because we're changing substances, get into the habit of writing that as part of your units as well. That's part of your answer. So 129 grams of nitrogen is your answer. Okay, hopefully you look at this and you think, okay, those were logical steps. You're just doing step by step in this. Okay, I'm going to go to the next one. Okay, here it says what amount of barium sulfate is produced. So I know my barium sulfate is going to be on this side, and it says we're reacting barium chloride with excess sodium sulfate. So at this point, do I just need to balance it now, or is there something else? There's something else. What else do we need to do before we can balance? It's a double replacement reaction, so we have to figure out, even though it didn't give it in the problem, we have to figure out what our other product is, because this does not obey the conservation of mass. We can't just suddenly have our sodium and our chloride disappear. So we see that the other product is sodium chloride. So in other words, you really have to look at your problem carefully and make sure that you write your reaction properly. So we balance it with a 2. And then we write down some information underneath. We're starting with, it says what amount of barium sulfate, so if it just says amount, that's kind of vague, but just assume it means grams if it says amount. And then we're reacting 2.34 grams of barium chloride. So there's what we need. Now we just set it all up, starting with what we're given. Our 2.34 grams of barium chloride. We don't want it as grams of barium chloride, so we convert to what? Moles of barium chloride. And we know 1 mole of any substance is equal to its weight in grams. I will add that up in my head ever so quickly and get 208.23 grams. I have a cheat sheet. Okay, so now we've got moles of barium chloride. Yeah, that's not what we want. So what do we need to convert it to? Awesome. Moles of barium sulfate. What number goes up top? Bottom? 1. Yeah, not very exciting. Doesn't change things mathematically. But it does get rid of the moles of the stuff we start with, and we get to the moles of the stuff we're looking for. So we're that much closer. So now we have our moles of barium sulfate. We want to get rid of that and be really careful and look at what it's asking for. It's asking for grams of barium sulfate. 1 mole of any substance is equal to its weight in grams. 233.4, I guess it's 40. We round, remember, to 2 past the decimal on our masses. So plugging it into your calculator, let's see what we get. Okay, so what are answers here? Anyone? 2.62 grams of barium sulfate. And again, we started with 3 sig figs, so we should end with 3 sig figs. Okay. Last one that is just our straight stoichiometry example. And you know what? I think I kind of skipped over this at the very beginning somehow as I was flying through that. That stoichiometry just means to measure. So it's Greek, to measure. And that's all we're doing is we're measuring things and we're looking at that mole ratio to go from one substance to another. So this is our last example that we have that's just stoichiometry without adding any new stuff in there. So it says what amount of barium sulfate. Again, this is going to be that same reaction. So we're starting with our barium chloride plus sodium sulfate, and we get barium sulfate plus sodium chloride, and there it is balanced. So in this example now, we're still looking for the amount of barium sulfate, but we're starting with 13.2 milliliters 13.2 milliliters of barium chloride, and that barium chloride is 0.875 molar. Remember, we just said molarity equals moles per liter. I would probably just keep it written like that when I write it underneath, but for the sake of this example, so you guys can think about what you're going to be doing in these next steps, maybe you want to rewrite these. Instead of having it as milliliters, what would be a better unit for this? Liters. So 0.0132 liters. All I did was move it 3 places to the left. I think you guys are now savvy enough with your dimensional analysis and knowing your metric conversions that you know that that's all you have to do. If you're not sure about that, feel free to throw it in your stoichiometry as a step where you have 1 liter equals 1,000 milliliters. And then remember, we said that in dimensional analysis, that big capital M is never going to cancel. So instead of the big capital M, what you want to have is moles per liter. So if it helps you to just see it written that way so that you know what to do, then maybe you want to write it that way when you put it underneath. So I'm going to have to start with one of these numbers. Do I want to start with 1 unit or 2 units? 1 unit, right. So we're going to start with 0.0132 liters, and this is barium chloride that we're starting with. I want my liters to cancel, so I'm going to put liters down at the bottom. What can I put up top? Moles. Moles. So the reason we started with our 1 unit is because this 2 units, we weren't sure if it was going to be moles on top, liters on the bottom, or liters on top and moles on the bottom. So by starting with your 1 unit, that's how you can figure it out. But you see 0.875 moles for every 1 liter. So we have just now successfully used both of these values and converted our barium chloride to moles. So now that we have it in moles of barium chloride, we don't want it as moles of barium chloride. We want to get to moles of barium sulfate. What number goes up top? 1. Bottom? 1. Again, that's it. So that is that step right there when you have that mole to mole ratio. And now that we've got it as moles of barium sulfate, you've got this information from the problem before. You want to just go to grams of barium sulfate, and you see that 1 mole is equal to 233.40 grams. And we plug it in, and I believe, I'm going to calculate it real quick. There we go. 2.70 grams of barium sulfate is what you should end up getting. So double check your answers there. Notice that it's 3 sig figs because you started with 3 sig figs in each of those. Okay, so now taking it a little bit further, we're still going to work with stoichiometry, but we're going to work with it for some gases as well. Note that this only works with gases. So um, when you're physically back in the lab, if I wanted to figure out an amount of a gas, it is hard for me to just put that on a balance and mass it and weigh that and get an answer. So instead of working in grams, it's much easier when working with gases to work in milliliters or liters. Because we're talking about some larger quantities, we're going to work with liters. So whenever it talks about volume, you guys need to figure out the volume of your gas in liters. And it turns out, and we'll be able to calculate why this is in another unit, but 1 mole of any gas has the same volume, and that volume you need to memorize, and that is 22.4 liters. This only works for gases. That's another key part of that. So 1 mole of any gas has a volume of 22.4 liters. Later on, we're going to stress that this is only at standard temperatures and pressures. So right now, just assume everything's at standard temperatures and pressures, even if it doesn't tell you. But later on, we'll talk about how that can change things. Okay, so that brings us to a new mole map. We said that we're not really going to worry about the number of particles anymore, so in its place I put volume. And again, if you can get to moles, you can easily convert from moles of one substance to moles of a different substance. So in this first example that we're going to look at, it says, we'll write it out first and then we'll go back to the mole map. What volume of chlorine gas can be produced, so I know chlorine's going to be over here, by the decomposition of sodium chloride. I'm going to rewrite this. Sorry. So I'm taking sodium chloride and I am decomposing it to sodium plus chlorine. So then I balance it, and that is it. So our problem says what volume of chlorine gas. I know when it asks for volume, that means liters. And it's produced by the decomposition. I'm starting with 5.63 grams of sodium chloride. Everything I need is right there. I don't care about any of this stuff anymore because everything I need is right in front of me. So if I'm going from grams of one substance to liters of a different substance, let's go back and look at our mole map. Grams of one substance to liters of a different substance. So think about that pathway, that train of thought that you have to take. You're going to go from grams of one thing to moles of that one thing, moles of one thing to moles of a different thing, then moles to volume in that last step. Okay, 5.63 grams of sodium chloride. Going to get rid of our grams of sodium chloride, go to moles of sodium chloride. So I look at my formula mass, 58.44 grams of sodium chloride to every 1 mole of sodium chloride. Now that we've got it as moles of sodium chloride, we want to go ahead and convert it over to moles of the other stuff. So we get rid of our moles of sodium chloride, go to moles of chlorine. What number goes up top? Bottom? Okay. So you guys looked at your balanced chemical equation. That's that step. Now that you've got it as moles of chlorine, what are you going to put up top? Liters of chlorine. What number goes with the liters? Good. And with the moles is just 1. So 1 always goes with the moles unless it's at this bubble step that I've been doing, that mole-to-mole transition step. And as an answer, anybody get one? 1.08, good. And that's liters of chlorine gas. Here's a common mistake that people make, and I mention this so that you guys are aware and you don't make this mistake. Lots of times people will be rolling along, and then all of a sudden they get to this last step and they say 1 mole of chlorine gas, yeah, that's going to be 35.45 times 2, and they put that as their mass up at the top. So really write this down, get into the habit of looking, what am I going to? I'm going to liters. Doesn't ask me for grams, so you'll get it wrong if you go to grams instead of liters. So really be aware of that type of stuff and don't make a simple little mistake like that. Okay, next one. Volume of hydrogen gas produced by the reaction of magnesium with hydrochloric acid. So we have magnesium plus hydrochloric acid. Obviously, it's going to yield hydrogen gas, but it's also going to yield magnesium chloride, so we have to be able to interpret that. We know how to predict our products, plus our hydrogen gas. And there's our 2. Volume of hydrogen. So here we are looking for liters in this case. And we know that we're starting with 35, we're starting with our hydrochloric acid, so we're starting with 34 milliliters. I'm going to go ahead and write down 0.034 liters, just because it's easier for me. And then I've also got this many molar. I would probably just write a big capital M, but if it helps you, write moles per liter. And so that's what we know we're starting with and what we're going to. What number should I start by writing down here? Okay, good. So we put our liters down there. We know we don't want liters. We want it as moles. I should have probably mentioned that this is HCl. So we're going to convert to our moles of HCl because we know that there are wrong number. We know that there are, actually I should have done that, I guess, 0.125 moles for every 1 liter of hydrochloric acid. You converted successfully to moles of hydrochloric acid. Get rid of those moles of hydrochloric acid and go to moles of the other stuff that you're looking for. So hydrogen in this case. Number that goes up top, 1, bottom, 2. So there's that mole to mole transition step. So now you've converted over to moles of your hydrogen gas. Yeah, that's not good enough. It's asking for liters. So you get rid of your moles of hydrogen gas and you go to your liters of hydrogen gas. 1 mole, 22.4 liters. We report it to 3 sig figs. And we get 0.04. Okay, 0.476. If it were just 4/8, that would only be 2 sig figs. So make sure you get all 3. These are the significant figures. Your zeros are both insignificant. And then that's going to be in liters of hydrogen gas. And a couple more. So hopefully at this point you're going, wow, I get this. It's just very logical, step by step. You're just following that mole map. Here it's asking amount of solid ammonium chloride that's produced. So that's going to be as a product by the reaction of ammonia gas and hydrogen chloride gas. So ammonia gas plus hydrogen chloride gas. Oh yeah, that's really just HCl. Hydrochloric acid, but it's just a gas. It's not mixed together with water as an acid. You know, it's not aqueous. It is a gas. So we are forming solid ammonium chloride. It is balanced already. So then we throw in the information underneath it. It's saying what amount of solid. So this is just going to be grams. Even if you looked at that and you weren't sure, amount, could it mean liters? Would you be able to put liters right there? Why or why not? It's a solid. It is a solid. So the answer is no. You can't put liters there. There's no question in your mind that it's got to be grams there because 22.4 liters does not work with a solid. So we're looking for grams, and we know that we're starting with this gas right here, our hydrogen chloride gas, and we have 975 milliliters. Oh, just for kicks, I'll do this one the long way. I would probably just start 0.975 liters, but in case you're not comfortable with that, you can start with this, and this is your HCl. You don't want it as milliliters, you want it as liters. You know that in one of these big things, there's 1,000 of these little things, so that's what you've got to have memorized. Again, this is your hydrochloric acid, or your gas. So now that you've got it as liters of HCl, what do you want to go to? Moles of HCl. So get rid of those liters and go to moles of HCl. 1 mole of any gas is equal to 22.4 liters. So you've got it as moles of this substance. We need to make it go to moles of this substance. So get rid of hydrochloric acid and go to ammonium chloride. Kind of boring, 1 to 1. That's that step. So now you've converted to moles of your new stuff, your ammonium chloride. What's your last step? To get rid of moles and go to grams. So just get into the habit of always looking up here again. What is it that you're looking for? Oh, it's going to be grams. So you add it up, and you get 53.03 grams of ammonium chloride to every 1 mole. And to 3 significant figures. 2 point what? 3 what? 1? I think that's right. 2.31 grams of ammonium chloride. Yay, last one. And for this last one, it says, what volume of steam can be produced by the combination of hydrogen and oxygen? So hydrogen plus oxygen yields steam, written as water. Balance it. Write the information down underneath. It says what volume of steam. So that's liters. That's a gas in that case. It's not as a liquid. And we're going to start by having 35 liters of hydrogen and plenty of oxygen for this reaction to take place. That's not going to limit how much we can do. And for this one, I'm going to choose somebody to do this. Okay, ta-da, it was done perfectly. So here we started with our liters of hydrogen gas, went to moles of hydrogen gas, got rid of moles of hydrogen gas, went to moles of water, got rid of moles of water, went to liters of water, which is what we wanted. And then we also notice, and this will take place every time you go from liters to liters, don't be freaked out, that your 22.4 is also going to cancel. That's it. So now you people without calculators, what's your final answer? 35, that's it. So 35.0 liters of H2O. You guys are done.